So in this video, we're going to look at right triangle trigonometry. If you're following along in the Blitzer pre-calculus book, I'm going slightly out of order because I want to start with something you're more familiar with. And if you've ever done anything with trigonometry and angles before, you probably remember something called SOHCAHTOA. So I want to start with what you're familiar with before we kind of get into really defining and dealing with these trig functions around our actual unit circle. So let's do a quick little review of what SOHCAHTOA was. So I drew a very sloppy right triangle. Let me try that again. A little bit better. So we have a triangle, and in that triangle, we're going to define an angle. One of the non-right angles. The right angle, we never do trig functions from a right angle. But do keep in mind that the trig function relationships that we're going to talk about only can be identified within a right triangle. Now, it doesn't matter. I could have put theta up here, but I chose the base angle for theta. That part doesn't really matter. It does change the trig functions a little bit, though, and we'll talk about that in a second. So what is trigonometry, and what are trigonometric functions? There are 6 trigonometric functions. They are sine, S-I-N-E, which we're going to identify as, so I'll write them out. This is the only time I'll actually write them out. But that one we identify as S-I-N. There's the cosine function, which we're going to identify as C-O-S. There's the tangent function, which we're going to identify as T-A-N, tan. So we have sine, cos, and tan. Now, we also have what we call the reciprocal of those functions. The reciprocal of sine is actually cosecant. And we would write that one as CSC. The reciprocal of cosine is secant. And we would call that one SEC. And then the reciprocal of tangent is cotangent, which is COT. And I know that's a little confusing because sine and cosine are not reciprocals of each other, but cotangent and tangent are reciprocals of each other. So it's just something you have to kind of get familiar with. What does any of this mean? Well, number one, you can only take a trig function of an actual angle. So for example, whenever we do a trig function, it is quickly followed by an angle. And that angle could be in radians or degrees, but because trig functions were initially defined in radians, we work in radians as much as we possibly can. And what does sine of theta represent? Well, it's a ratio. If I'm talking about the sine of theta, I'm talking about a ratio. So in order to do these ratios, I'm going to need to put some letters around my triangle, right triangle. You're all familiar with a squared plus b squared equals c squared. And in that format, we're going to call c the hypotenuse of our right triangle. I'm going to put my a over here and my b down here. So all I did is a very traditional labeling of that particular right triangle. So sine of theta, well, again, sine is a ratio. It's a ratio of 2 sides of our right triangle. Well, which 2 sides? This is where this little phrase comes into play, and you may remember it. Sine is opposite over hypotenuse. Opposite over hypotenuse. So it's the opposite side over the hypotenuse, which in this case would be A over C. Now keep in mind, it is defined from where the angle is. It is defined from where the angle is. If, and I'll do it down here, if I chose same labeling, but instead of putting that theta down there, I put it up here, then sine of theta would be B over C. So again, you got to be careful because it comes from wherever the angle happens to be. And in our triangle that as I have written right now, it's A over C. And let's talk for a minute about what I mean by opposites. So here's my theta. B or C cannot be opposites because they are the terminal and initial side that form theta. The opposite has to be directly across, or what we'd say it's not actually touching the angle. The hypotenuse is always the side that is across from the right angle, and adjacent refers to the other leg, not the hypotenuse, that helps form the actual angle in question. So you got to be careful. What is opposite, what is adjacent, and where is all dependent upon where your angle actually is. So for example, just to do one more, let's suppose I'll do it in green. I call this angle up here alpha. Okay, so let me define those real quick. We call this theta. It's a Greek symbol. We use Greek symbols for a lot of different things in mathematics. And this one is called alpha. And we will use those two representations for angles very often in this class. So do get used to those symbols, what they are and what they look like. All right. So as I said, what if I called alpha up there? Then sine of alpha is actually, it's still opposite over hypotenuse. That does not change. But from alpha, the opposite side is actually the B, and it becomes B over C. So again, be careful. It is very dependent on where it is and what angle you are referring to. All right, so I'm going to erase this because we're going to stick now with theta. Cosine, come over here, cosine is actually adjacent over hypotenuse. Which would be B over C based on where our theta is. And tangent, can take a look at this. Tangent is opposite over adjacent. So opposite, of course, is A. Over B. Yeah. Do whatever you need to do to commit all that to memory. That's all I'm going to say. Remember your SOHCAHTOA. Do whatever it is you need to do. You won't make it very far in this class if you cannot get all of that committed to memory kind of ASAP. And like I said, just remember your SOHCAHTOA. Many of you have probably experienced at least this much in a high school geometry class, so hopefully it's just a matter of getting refamiliar with it. Now let's talk about the reciprocal. Why are these called reciprocal identities? Because cosecant, well, that's going to be hypotenuse over opposite. So that's C over A. Secant is adjacent over opposite over hypotenuse, sorry. I don't know what I was thinking there. I apologize. Hypotenuse over adjacent, so sorry. And that's going to be C over B. And cotangent is adjacent over opposite. And that's going to be B over A. So you can see the fractions are reciprocals. So, well, what is our right triangle trigonometry? So, for example, let's start with a very simple triangle. If that's a 3 and that's a 4, one leg 3, one leg 4, you might remember something called Pythagorean triples. There happen to be these magic numbers where all 3 sides of a right triangle are whole numbers. Or you can just quickly apply the Pythagorean theorem, something you're going to need to do a lot when you are given 2 sides of a right triangle. In this case, you're given the 2 legs, so 3 squared plus 4 squared. It's 9 plus 16 is 25, and the square root of 25 is 5. All right, so you're given that information. And let's come up here, and let's do alpha, and let's put alpha up there. So what does that mean? Sine of alpha. Sine of alpha is, opposite over hypotenuse. So 3/5. Cosine of alpha will be adjacent over hypotenuse, 4/5. And tan of alpha will be opposite over adjacent, or 3/4. And then, of course, cosecant of alpha, 5/3. Secant alpha, 5/4. And cotan alpha is 4/3. So they're simply the reciprocals. Now, do we know what alpha actually is? Well, no, we will learn how to figure out what alpha actually is on our calculators. That is something we can do and we will do eventually in this course. But if you are curious, if I were to do it in degrees, alpha looks like it would be about a 37-degree angle, just in case you were curious. I'll double check that by doing one of the other ones. And again, we will get to the point where we can actually use these trig functions to calculate. But yeah, it would be about a 37-degree angle. But you don't need to know that just to get the ratios. All right, so what does that mean? Well, that means the sine of a 37-degree angle is about 0.6 or 3/5. All right, that's kind of what that is telling you. Now, there are some angles, though, that are used so commonly and allow us to get exact answers to various things. Because if I were to take sine alpha, it comes to actually sine alpha equals 3/5 to actually figure out alpha is. It is actually, it's like 36.8 blah, blah, blah. It's this big irrational number. Okay, so we have a couple angles we really like to work with a lot. And I want to go through those angles. Okay, and if you won't be surprised, they're angles that we've kind of already worked with. So the common angles I want to work with are pi over 3, pi over 4, and pi over 6. So you might remember from the last lesson, pi over 3 is a 60-degree angle, pi over 4 is a 45-degree angle, and pi over 6 is a 30-degree angle. And throughout this course in trigonometry, we're going to be able to do a lot with combinations of those angles. So what we have are two triangles that help us to represent these particular angles. The first one, we name it in degrees. It's called the 30, 60, 90 degree triangle. Because it's really kind of hard to say the pi over 6, pi over 3, pi over 2 degree radian triangle. So we call it the 30, 60, 90. But you have to be familiar with it not only in degrees, but in radians. So what does a 30, 60, 90 look like? Well, first of all, a 30, 60, 90 has a short side and a long side. Let's draw it the other way. I like drawing it the other way better. So I'm going to draw a long side. So it's got a long leg and a short leg. And it is a triangle that has, now if you remember your basics about triangles in general, the shortest side is always across from the shortest angle. So my 30 degree would be here. And then my 60 degree would be up here because the is always across from the largest. Now, putting that in radians, what would that look like? Well, the pi over 6 would be here, and the pi over 3 would be up here. So same exact triangles, one's in degrees, one's in radians. Now, we actually have a relationship for the sides of these triangles. So let's see, because again, you are going to need to, this is one of those other things you're going to need to memorize. So as you're building it, this is how I want you to think about it. When you go across from the short side, you put a 1. The shortest side is 1. Hypotenuse is double that. And this is radical 3. And it works. You can apply Pythagorean theorem to it and see that it does indeed work and fits your Pythagorean theorem. So I tell students when you take tests and do everything else, this is the one right here you want to basically copy immediately onto your test. That takes care of this angle and that angle. But for the 45, we have a new triangle. That's our 45 degree 90 triangle. Well, that particular triangle, as you can imagine, since they're both 45 degrees, is what we call an isosceles right triangle, where two legs are the exact same. So 45, and then of course, to put it in radians, it would be pi over 4. And we set this one up to easily make each leg 1, then use Pythagorean theorem, you get radical 2. Now, again, another angle that you do need to, another triangle you need to memorize. These two triangles you should draw immediately. I would draw them in radians because radians is what you're going to mostly be working with on every test throughout the whole semester when you first get the test, because that's how much you're going to be using these particular triangles as we work through our trig functions and learn different rules and procedures around these trig functions. So that doesn't mean, you know, when you, this is a set of ratios for the side. So for example, if you expand the triangle, the ratios, the relationship between the sides remain the same. So I'll do it in red. For example, if I made this 5, 5, in other words, I multiplied 1 by 5, this would become 5 radical 2. radical 2. I don't know why I wrote 5 radical 5. 5 radical 2. All right. Similarly, with the other one, if I multiplied that one by 5, right, that would become 5. That would be 10. And that would be 5 radical 3. But because we're dealing with ratios, we can use the most basic ratios. And when I say the most basic, all I did is start with the shortest side of each rectangle and just made it a 1. And then took it from there. But again, it can be, you can make any of it it doesn't matter. The relationship doesn't matter because as we work through trig functions, when we put opposite over hypotenuse, it ends up being exactly the same. So for example, let's suppose instead of having a hypotenuse of 2, I went to 1. In other words, I cut it in half. Well, if I cut 1 in half, that becomes 1/2. And if I cut square root of 3 in half, it becomes square root of 3 over 2, right? It doesn't matter what set of numbers I use. The sign is going to be the same thing. Let's take a look. Let's do sine of pi over 6. Well, I'm going to use the numbers in black first. Sine, we just learned, is opposite over hypotenuse, so sine of pi over 6 is simply 1 over 2. Well, what if I use the numbers in red? Sine of pi over 6 will be 1/2 over 1, which again is still a half. So again, doesn't matter how we use the numbers as long as they're in the same ratio, and it's just easier to use them where the smallest side of each triangle is a 1. It's easier to memorize, it's easier to reconstruct when you get your test and everything else. Okay, so that being said, we can use these triangles to come up with sine, cosine, and tangent. I'm not going to go through the reciprocal functions because you can simply do that by taking the reciprocal of the function it's the reciprocal of. But these are so common that many students simply memorize them, though I think if you just recreate these two triangles, it's easier for me to memorize those triangles than it is to memorize an entire chart. But we can use this, and you'll see these charts in your notes and stuff like that. But let's take a look. For different theta, I can do pi over 6, which we know equals 30 degrees. I can do pi over 3, which I know, let's do pi, we'll do them in order. Pi over 4, which is 45 degrees. And I can do pi over 3, which is 60 degrees. Now, I can get the sine, cosine, and tan of each. So let's start with, shrink it down a little bit so we can see the whole thing, sine of pi over 6. We'll go to sine of pi over 6. That's simply going to be 1 over 2. Opposite over hypotenuse. Let's continue with sine. Let's do sine of the 45-degree angle, or sine of pi over 4. Well, I'm going to do this one off to the side for a second, because when I do sine of pi over 4, I get 1 over radical 2, opposite over hypotenuse. We are going to rationalize these radicals. So how do I do that? Well, I got to multiply by radical 2 over radical 2, so it actually becomes radical 2 over 2. And then sine of 60, or sine of pi over 3. Well, to get that one, I have to come up here, right? So again, based off going from the pi over 3, my opposite is now radical 3 over 2. Now we can do the exact same thing for cosine. So I'm going to go through this one a little bit quicker. Cosine of 30 degrees, well, that's square root of 3 over 2. Cosine of 45, well, that is also 1 over radical 2, which is 2 over radical 2, or radical 2 over 2. And then cosine of our 60-degree angle, or pi over 3, is 1/2. Tan of our 30 degree is going to be 1 over radical 3, But when you do 1 over radical 3, you need to rationalize, and that becomes radical 3 over 3. And tan of our 45, oh, wait, that's just 1 over 1, which is simply 1. And then tan of our 60 degree is square root of 3 over 1, which is square root of 3. So again, some students actually memorize the chart, but I kind of find it easier to just write these two triangles down, and then I always have them as a reference when I'm doing problems on our test and everywhere else. So we use our right triangle trigonometry to come up with these special angles and the sine and cosine and tan. And again, you know, if we needed cosecant of 30, you would just do 2 over 1 because it is the opposite of sine, the reciprocal of sine. This is such an important piece that I do want to make sure you understand how to recreate them and how to be able to get the trig functions of those. But you can also see some kind of cool relationships, right? Take a look. What's the relationship between pi over 6 and pi over 3, or 30 degrees and 6 degrees? They're complementary angles, right? Because they are the other two angles of a 90-degree right triangle. They're complements of each other. They add up to 90 degrees. Well, do you notice that the sine of 30 is the same as the cosine of 60? Well, that is certainly not a coincidence. That actually leads us to one of our first identities, and we'll get into identities in the next video. We'll get into some more identities. You kind of already know your reciprocal identities because the reciprocal identities are just stating that cosecant is the reciprocal of sine and so on. But we'll do more identities in the next video. But this is something called cofunction identities. And the way cofunction identities work is, just like we said, sine of one angle is equal to the cosine of the complement of that angle. And that goes both ways. Cosine is the okay. Now, that also works for tan and cotan. And it goes for cosecant and secant, because that's what they mean by cofunctions. So sine and cosine certainly do have a relationship. They have a cofunction relationship. So this little relationship can come in handy at different times. Let's take a look at an example. So find a cofunction with the same value as the given expression. So we'll keep the first one easy. Sine of 72 degrees. Well, sine of 72 degrees simply equals the cosine of 90 minus 72 degrees. And you would finish that, you wouldn't leave it like that, which is the cosine of 18 degrees. So if you know the sine of 72 degrees, you also know the cosine of 18 degrees. And let's do cosecant of pi over 3. Well, that equals secant because that's a cofunction. Cosecant and secant are cofunctions. of, well, I'm not going to put 90 there because I'm working in radians. I would use pi over 2 for 90 minus pi over 3. Well, if I put them both over 6, right, that's secant of, put them both over 6, so that's 3 pi over 6 and 2 pi over 6. So 3 pi over 6 minus 2 pi over 6 is secant of pi over 6. Or you could have seen above. You will get in the habit of knowing that pi over 3 and pi over 6 add up to 90 degrees together. Okay, so I'm going to end this, and we're going to do a separate video after the next one that'll deal with more of applications and calculator usage when it comes to trig functions. But I did want to have you watch this prior to our unit circle video, which will be a pretty big and might even be in 2 parts, the unit circle video, because I think it's important for you to just start with what you remembered from high school, which was SOHCAHTOA.